scientists have just made a remarkable leap in quantum computing. They've linked nuclear spins inside silicon chips, opening a new path toward truly scalable quantum machines. At the University of New South Wales, engineers created what are called quantum entangled states. In this mysterious phenomenon, two particles become so deeply connected that their behavior can no longer be explained independently. The team achieved this using the spins of two atomic nuclei, an essential building block for quantum computers to one day outperform today's machines. Their results, published in Science, mark a crucial milestone in one of the greatest scientific frontiers of our time. Lead author Dr. Holly Stemp explains that their work points to a future where quantum microchips can be built with technology that already exists. We succeeded in making the cleanest, most isolated quantum objects talk to each other, at the very scale used to fabricate today's silicon devices, she says. The challenge, until now, has always been balance. Quantum states must be protected from noise and interference, yet they must still interact in order to compute. Too much noise, and the system collapses. Too much isolation, and it cannot perform calculations. For years, UNSW researchers pursued the second camp, highly isolated nuclear spins. Phosphorus atoms, implanted in silicon, became their tool of choice. As Professor Andrea Morello puts it, the spin of an atomic nucleus is the cleanest, most isolated quantum object in the solid state. The team had already shown that quantum information could last for over 30 seconds, an eternity in the quantum world, and that their operations had less than 1% error. But there was a catch. The very isolation that protected nuclei made it extremely difficult to connect them into larger processes. Until now, the only way was to place nuclei very close together, tied to the same electron. It worked, but it did not scale. Dr. Stemp offers a vivid metaphor. Nuclei were like people placed in a soundproof room. They could talk clearly inside that room, but they could not communicate outside, and only a few could fit. The breakthrough changes everything. It's as if we gave them telephones, she continues. Now they can talk across rooms, still enjoying peace and quiet, but able to connect with many more. In this story, the telephones are electrons. By spreading out in space, electrons allow distant nuclei to communicate. As co-author Mark van Blankenstein explains, two electrons can touch each other from afar, and through this, the nuclei linked to them begin to talk. In the experiment, the nuclei were about 20 nanometers apart. That may sound tiny, but scaled up to human size, it would be the distance between Sydney and Boston. Even more striking, 20 nanometers is exactly the scale of modern silicon chips. The same chips that already run in billions of smartphones and laptops around the world. That's the true breakthrough. Clean, isolated quantum objects communicating at the same scale as existing semiconductor devices. Suddenly, the trillion-dollar infrastructure of the silicon industry becomes a foundation for quantum computing. Despite the exotic physics, these devices remain compatible with today's chip-building techniques. Ultra-pure silicon came from Japan, phosphorus atoms were implanted in Melbourne, and UNSW brought it all together. By removing the requirement that nuclei must share the same electron, the team cleared the biggest roadblock to large-scale silicon quantum processors. And the road ahead looks promising. Our method is remarkably robust and scalable, says Professor Morello. Here we used just 2 electrons, but in the future we can add more, shaping them to spread the nuclei even further. Electrons, he adds, can be moved, tuned, and switched on and off with precision. Exactly what is needed for a quantum computer that can grow from tiny steps to a universe of possibilities. With this breakthrough, quantum computing takes one step closer to leaving the lab and entering the world, transforming silicon chips from the backbone of classical technology into the foundation of the quantum future.